Good afternoon, sir. Myself, Aditya Fukan. I'm from the Mechanical Engineering Department, 6M. So my problem was problem 16 that stated that we have to simulate steady state 2D laminar flow in a channel with symmetric parabolic inlet velocity profile in Ansys Fluent. So I have already opened the Ansys workbench. Now we'll select the Fluent. So now first we'll do the sketching in the geometry. For that we have to right click and then open the new design modular geometry. So here it is, the design modular geometry, where you can sketch our rough sketch. So we will select our plane and then sketch rectangle, select a origin and then click on it. Now we'll give our dimensions. Let's say the dimension is, the horizontal is 1 meter and the vertical will be 0.1 meter. So we have given our dimensions, and here is our rectangle or the channel. Now we'll surface from the sketch, select one line and then apply and generate. So it is our sketch. I will close it. Now we'll proceed towards meshing. For that, to double click it. So here is our rectangle. Now let's define our material. So here it is solid. We'll change it to fluid. Now for meshing, we'll generate a mesh. So it is generated. We'll give the element size as 0.01 for more accuracy and better results. Generate. Now we'll give insert the refinement, select the sketch and then apply. Generate. So the meshing is done. Now we'll name our edges. So click on the edge and then click on the inlet, press N. We will name this as inlet. Similarly, the outlet, here is the top wall, and lastly the bottom wall. So the meshing and the name selection is done. So now we can proceed further. So let's close it, update the mesh. It's taking time. Here is the progress. Okay, now it's done. Let's proceed to the setup. So we have to select double precision and then start. So here we can see the outlet channel. So here the settings will be default as it is steady, planar, absolute, and it will be solved on pressure based solver. So now we'll turn on the energy equation. Next we'll change the viscous to laminar flow. Now we'll proceed to name expressions. We will define our parameters. So here click the new and then name it as h for the height, that is 0.1 meter. Press OK. Again new. Now we'll give the velocity, that is u max, that is 0.1 meter per second. Press OK. Now we'll give the final expression, that is say u inlet. So let's write the expression 4 into u max into y to bracket h minus y bracket close divided by h square. Press OK and close. So now we'll proceed further. Now we'll give our boundary conditions. Double click on inlet. We have to change this magnitude normal to boundary to components, and x velocity we have given, that is u inlet, and then apply. We have to close it. Now we'll initialize it. So go on initialization, hybrid initialization, and then initialize. So here it is showing that initialization is done. So now we can proceed to calculation. So we'll click on it. We'll give number of iterations as 500 and then calculate it. So calculation is complete. Now we'll quit it. So 4 steps are done. Now we can proceed to results. So double click it. We'll go here, insert, then contours. We will name it as temperature contour. We'll change the variable pressure to temperature, and then locations bottle 1 to symmetry 1. Now of contours we have to change it to 50. Let's say 50. It can be anything, it's of your choice. So now let's apply it. So here is the temperature control in adiabatic condition. Now let's do it for the heat flux. So let's copy it. The settings will be same for both of the cases, but in the setup we'll change the heat flux. So let's say it was for temperature in medium. So let's open setup, same as the previous one. So here we will change our inlet and top wall and bottom wall's parameters. So in the boundary condition, select wall and bottom wall, go to thermal and change the heat flux from 0 to 1000. Do this same for the top wall also. Thermal heat flux, that is 1000. So now close it. Again we have to initialize it. So initialization is done. Now calculate. So the calculation is complete. We'll now close it. Now we'll open the results. So here are the results of the heat flux. This is the heat flux in the previous one. This is the temperature control in adiabatic conditions. Here the temperature will not vary as it is adiabatic. No heat will transfer from inside to outside or outside to inside. So here is the adiabatic condition, and this is the heat flux. So thank you. That's all.